Welcome to the module Electricity and Magnetism. Today I'm going to tell you about electric forces and fields. And of course, electricity, electric forces, and electric fields are omnipresent around us. For example, as you see on this beautiful picture of lightning hitting the Earth due to a very strong electric field due to build-up charges in the sky. Not only can we see it there, but also, for example, there's this very memorable things, all of us have done this, where we take a balloon, we do it to ourselves or to our little brother, and our hair goes all the way up. This is how we charge our own hair, but for example, if we go into the mountain, sometimes, due to the shape of the mountain, there's such a strong electric field that our hair miraculously stands up. And in this case, we can wonder, what are the forces that the hair exert on each other? So these are the things we're going to talk about in this lecture. So, electric forces. All of us have, one way or the other, heard about electric forces around us. For example, if we have one charge, in this case it is Q1, and another charge Q2, at a certain distance among each other, we all know that if, for example, Q is positive, Q1 is a positive, and Q2 is negative, that they will attract each other. As we can see here, there are also other cases. For example, if we have two equal charges, two positive ones, they will repel each other. Or if they are both negative, they will also repel each other. But if we have a positive and a negative charge, they attract each other. So far, very little new. I guess you feel you just finished your high school education, you know this. But as scientists and as we are in university, our aim is to take this to the next level. As already 300 years ago, Mr. Coulomb did at the end of the 18th century. So Coulomb asked, rather than does one negative charge attract a positive one, he asked how much does a negative charge attract a positive one? Can we calculate this? Can we measure it? So what Coulomb did, that he designed a very clever experiment. So in this experiment, basically, he had as we can depict it in the picture on the slides, there is a spring that's connected to two red balls. In this case, they are negatively charged. They can rotate and thereby actually push on the spring, so force gets exerted. There's also a blue ball, that's the opposite charge, and that basically the blue and the red ball exert a force on each other. Now what he did, which was very clever, he basically rotated the blue ball away from the red ball or close to it, and thereby he varied the distance between the two charges, and he measured with the spring the force that one exerted on the other. And by doing this experiment, he could actually find a quantitative relationship between the attraction or repulsion between two charges. So what did he find? What he found was the very famous Coulomb's law. And what Coulomb's law tells us is that the force of one charge Q1 on another charge Q2 basically scales as Q1 times Q2 divided by the distance between them squared, multiplied with a constant K. And to recognize Coulomb for his beautiful law, this law was basically named after him, but also the constant K is what we call the Coulomb's constant. And we also say that the amount of Q, the unit of Q charge, is basically Coulomb. So we have Coulomb's law, the unit of charge is Coulomb, and the K is the Coulomb's constant. So now we know how much one charge attracts or repels another charge. However, that's not the whole story, because as I just showed you, two positive charges repel each other, as do two negative charges, but a positive and a negative charge attract each other. So there's also a direction between those interactions. And this is what you can see below. So you see that Q1 actually exerts a force on Q2 that's in the direction of R. R is the vector from Q1 to Q2. And as we can see in the equation I wrote below it, is that F of Q1 on Q2 is actually this K Q1 Q2 divided by R squared multiplied with R hat. And this is something that's new to you. And before I go on to this, I would like to stress that we also have the opposite force of Q2 on Q1. And because R hat is still this vector in the same direction, as a consequence, this needs to be minus K times Q1, Q2 divided by R squared multiplied with R hat. Okay, so now we went very rapidly from something very obvious that two forces attract each other to something as complicated as R hat. Let me tell you, it's not that complicated. What in the end R hat is, it is the unit vector of R. So what that means, it's actually a vector, a direction with a length of 1. So that means that we have the vector R, so this is R with this arrow, and the vector R points from Q1 to Q2 with a length of R. But the unit vector R hat is actually normalized with the length of R, which is this R between vertical lines, the length of R. So basically R hat is what we call the unit vector of R. So if we go back to our equations, what we see is that basically this force of Q1, Q2 is basically in the direction of R. So it's basically with R hat. And it still scales as 1 over R squared. And the opposite is the case for the force in the opposite direction. So I told you about the magnitude of electric forces and about their direction, but another important aspect of electrical charges is the fact that they're quantized. So basically, when Coulomb found out that there were these electric forces exerted on each other, he did not know that actually electrons existed. And only 300 years later, Mr. Millikan in a very beautiful experiment found that the fundamental electric charge, so the smallest possible charge, is actually 1.6 to 10 to the power 19 Coulomb, which is basically 1 electron or 1 proton. Or for example, for hydrogen that has 1 proton and 1 electron, it is 0. And for helium and sodium, it's either 0 or plus 1 charge. So I told you about electric fields in the beginning. So an electric field is very closely related to an electric force. So a force is basically the force of 1 charge on the other one. And why we introduce electric fields is because an electric field is basically universal. So what you basically say is, if I know the electric field, then for any charge in that field I can calculate the force. So it's basically the force divided by the charge of my object. So the electric field, therefore, because it's the force over the total charges, it is Newton per Coulomb. And although sometimes this can feel a bit unintuitive, an electric field, we don't really see it around us. We sometimes hear about these 5G fields and they are maybe bad for us or not, but we are not seeing them. So I would find it usually useful to make the comparison with a gravitational field, where also this field we cannot see, but we can observe that apples, if they are loosened from the tree, they fall on the ground. So to take this analogy a little bit further, if I have a motor crosser and it basically drives over a ramp, if the conservation of impulse would say it would go in that direction forever. However, because of a gravitational force, it will go down and basically land a little bit further again, which is the same for basically a positive charge going into an electric field. If it is basically injected under an angle in a field, it will get deflected and go out into another angle. So with that, we can make the equivalent between gravitational force, where basically force can be calculated as the mass times the acceleration due to gravitational force. For an electric force, it's basically the charge multiplied with the electric fields. With that, I come to the end of this unit, and I wish you good luck with the following example in your exercises.